We just saw the unitary sodium current. Now let's have a look to the total sodium current, the sodium current that goes through the whole membrane, because this is this total current that underlies the action potential. To get this current, we record in whole cell configuration and to record the activity of the whole membrane, and in voltage clamp mode to record a current. So we record the activity of a large number of sodium channels. We add potassium and calcium channel blockers because these also are opened by membrane depolarization. They are also voltage gated. So to get only the sodium current, we have to block the other channels. Here is the current that we record in nanoamps, you have the scale here, in response to a step, a depolarizing step to minus 30 millivolt to be beyond the threshold of sodium channel activation or opening. We see two phases in this current. That is called activation and here inactivation. So this current is inward, it's negative. It's an inward current at minus 30 millivolts. And you have a rising phase, though it's negative, we call it a rising phase, up to a peak, and then a decay phase. Why? Because the rising phase represents the openings of the different sodium channels. They are not always at exactly the same time, so if you sum here all the openings with a variable delay, you have the rising phase, which is quite sudden, but not completely a straight vertical line, because it takes some time for all the channels that have to open. Here, the peak is where you have the maximal number of channels open at the same time, and then the decay, which is due to the inactivation of the channels that once they have opened, they inactivate, and the first to inactivate are the first that open. Now, if we give depolarizing steps of various amplitude, if we increase these depolarizing steps, what do we get? We get what we call a family of currents. So here we increase the amplitude of the depolarizing step in green, and we record the activity, the current, total sodium current in response to these different depolarizing steps, and you see now the current inverted, reversed. On the right, we have the IV curve. Each point represents the value here at the peak. So this here is the maximum here, and the value at each peak, and here, for example, this is this value here. So if you remember, the IV curve for the unitary current was a straight line. Here, it's a U-shaped curve. Why? Because for the unitary current, either the channel opens or not. Here, the channels, since we have many channels, they open gradually. So you remember that the whole cell current equals the unitary current multiplied by the probability of opening and the number of channels in the membrane. So this n is the number of sodium channels in the membrane. This is the probability of opening. And this probability of opening increases with membrane depolarization. So here in this first part that we call the rising phase, there are two opposing forces. One is the driving force, which decreases as we depolarize the membrane because we go closer to the reversal potential, the equilibrium potential, which is here. And from minus 60 to plus 40, the driving force decreases. But at the same time, on the first part, the probability of opening increases. So this is the one which wins, so that now the current increases in amplitude. The current increases in amplitude to a peak of the IV curve, where the probability of opening is maximal here. And then the current decreases. Why? Because all the channels that should have opened had opened. And now there is only the effect of the driving force. So the current decreases, and then reverses here at the reversal potential, and then you can, it is then outward. Oh, you remember that when we calculated the reversal for sodium ions in the first chapter, it was nearly plus 60 millivolts. Here it's 30. Of course, it depends on the concentrations of sodium ions on either side of the membrane.